In this lecture, we're going to be talking a little bit more about how derivatives affect the shape of a graph. So in class, we talked a little bit about the first derivative test, and how the first derivative relates to where our graph is increasing and decreasing. Now we want to talk a little bit about concavity, and then we're going to do some examples where we use these concepts together. So remember that a graph is going to be concave up. It looks something like this, or perhaps, let's see, something like this, when we have our tangent lines lying below our curve. So these are examples of concave up. And our graph will be concave down, looking something like this or like this, when our tangent lines lie above the curve. And one observation that we make with this is when we have our graph being concave up, we can see, for example, here, that our slopes are becoming bigger and bigger and bigger, so our slopes are increasing. Also here, even though our function is decreasing, our slopes are becoming less negative, so our slopes are also increasing. So here we have slopes are increasing. And here, when we're looking at these pieces of the function that are concave down, we see that what's happening is our slopes are becoming less steep. Less steep here. Here they're becoming more negative, okay, but in that sense they're also decreasing. So in both of these examples, the slopes are decreasing. So if the slope function is an increasing function, we're saying that f prime is increasing. Okay. Well, then using the relationship between a derivative and where a function is increasing and decreasing, we can say that f prime is increasing corresponds to the derivative of the derivative being positive, and where slopes are decreasing, in other words, f prime is decreasing, corresponds to that derivative being negative. So this gives us what's called our concavity test. So if our second derivative is positive for all x in an interval, then the graph is concave up on that interval. And if our second derivative is negative for all x in an interval, then our graph is concave down on that interval. So now we have information about where our graph is increasing and decreasing, where it's concave up and concave down, where we have local mins and local maxes. And there's one other piece of information that we can get from the second derivative, which is connected to this concavity idea. So another special point on our curve is going to be called an inflection point, and we have an inflection point wherever a curve changes from being concave up to concave down, or from concave down to concave up. So we have an inflection point where one of these changes of concavity occurs. So for example, if I had a sign chart here for my second derivative, and my second derivative went from being negative to positive, I know that that would mean my graph of f would be going from being concave down to concave up. And if I had this kind of switch, then I'd have an inflection point at x equals c. So what this might look like in a graph, let's see, I've got something that's concave down and then concave up. So I have something like this and then like this. So here at c, I have this switch from being concave down to concave up. So that's an inflection point. If I have something that goes from being my second derivative goes from being positive to negative at c, that means my graph of f was going from being concave up to concave down. So what this might look like is something that's concave up and then concave down, something like this. So here's another example where I would have an inflection point. We're also going to see that where an inflection point occurs is also relevant to where f prime has a max or a min. Because notice that if I have, let's see, we'll do this example here. You know, I've got my second derivative and it's negative and then positive. Well, that means that f prime, using the increasing-decreasing relationship, would be decreasing and then increasing. So when I have my second derivative change from negative to positive, that would be where my first derivative would have a local min. So I can also use information about my inflection point to say something about mins and maxes of the rate function, or of the function f prime. Okay, so we want to put this information together and talk about, given a certain function, how can I find, or I would like to find, where this function is increasing and decreasing, any locations of mins and maxes, where it's concave up and concave down, as well as any inflection points. Okay, so the first thing I'm going to need to do is take my derivative. Okay, so here I've been given a quotient, so we're going to have to use a quotient rule. So I'm going to have my bottom function times the derivative of the top minus the top function times the derivative of the bottom, all over the bottom function squared. So this is going to be x squared plus 1 minus 2x squared, so that's going to end up giving me 1 minus x squared, all over x squared plus 1 squared. Okay, so to answer these first two pieces about local mins and local maxes and where it's increasing and decreasing, I'm going to use that first derivative information. It also will be helpful for us to note what the domain of this function f is. So looking at this, I see I've got x squared plus 1 in the denominator, so that means that there's no way for x squared to be negative 1, so the domain is in fact all real numbers. So our function is continuous everywhere. So now I need to identify where this derivative is equal to 0, and that will only occur where this numerator is equal to 0. So I just need to look at where 1 minus x squared is equal to 0, and I see that would happen when x is negative 1 or positive 1. So I'm going to be looking at a sign chart here that has negative 1 and positive 1 on it for f prime. So I want to identify what's the sign of f prime in each of these three different intervals. So if I plug in something like negative 2 into f prime, well, negative 2 squared is going to be positive 4. 1 minus 4 is going to be a negative number, and this denominator, since it's squared, is always going to be positive, so I'm going to get a negative, since a negative divided by a positive is negative. If I plug in something like 0, I'm going to have 1 minus 0 is 1. Divided by a positive, so that's going to be positive. And if I plug in something like 2, again, my numerator is going to be negative, my denominator positive, so I'm going to have a negative sign. So this tells me that my function f is going to be decreasing, and then increasing, and then decreasing. So if I wanted to list these intervals of increase, f is increasing on negative 1 to 1 on that interval, and it's decreasing on the intervals from negative infinity to negative 1, as well as from 1 to infinity. So what about local mins and local maxes? Well, it looks like I've got a local min at negative 1. So at negative 1 comma f of negative 1. So if I plug negative 1 in here, so let me write f of negative 1, just to emphasize that we're plugging that negative 1 for the location of the point of the local min back into the original function. So if I plug negative 1 into there, I'm going to have negative 1 over negative 1 squared plus 1. That'll be negative 1 over 2, so negative a half. And I see that I'm going to have a local max at 1 comma f of 1, which turns out to give me 1 comma a half. So I have these 2 points of my local min and my local max, and my intervals of increase and decrease. So now I'm also going to need to use my second derivative to give me some information about concavity and inflection points. Okay, so now I'm trying to do this part because we've already done these two pieces. So remember that my first derivative was 1 minus x squared all over x squared plus 1 squared. So I'm going to have to take the derivative of that now using the quotient rule again. So my second derivative will be equal to x squared plus 1, squared. That's our bottom function, times the derivative of the top function, which is negative 2x, minus our top function, times the derivative of our bottom function. And we're going to have to use the chain rule there. So we're going to have 2 times x squared plus 1 times 2x. And then this is all over that bottom function squared. So x squared plus 1 to the 4th. So now I have to do a little bit of algebra. But I also notice that I have x squared plus 1 here, and I have an x squared plus 1 squared here. So I can factor out an x squared plus 1. So I have x squared plus 1 times x squared plus 1 times negative 2x minus, well, this is a 4x times 1 minus x squared, all over x squared plus 1 to the 4th. Okay, so taking out that x squared plus 1 out of each of those left me 1x squared here and no more x squared plus 1's here. So these cancel, so I've got something over a third power in the denominator. So let's see. If I multiply this through, I've got negative 2x cubed minus 2x minus 4x plus 4x cubed all over this x squared plus 1 to the third power. So this simplifies to 2x cubed minus 6x all over x squared plus 1 cubed. Okay, so that was a little bit of work, but we got our second derivative. So now I need to know, where is this second derivative equal to 0? Well, it's only going to be 0 where that numerator is 0. So that's where 2x cubed minus 6x is 0. So with a little bit of factoring here, I have 2x times x squared minus 3 is 0. So I see it's going to be 0 at 0 and also at plus or minus the square root of 3. Okay, so I have this sign chart for my second derivative where I have values negative root 3, 0, and root 3 on there. Okay, so now I have to think, what happens when I plug in something less than negative root 3? Well, if I plug in something like negative 2, I'm going to get something that's negative. Okay, so because, let's see, if I plugged in negative 2 into the denominator, that's always going to be positive. Negative 2 here, that's going to give me a negative 16 plus 12, but that's still going to give me negative 4, so I'm going to be negative. If I plug in something like negative 1, I'm going to have a negative 2, let's see, plus 7, so that's going to be positive. Again, if I plug in something like 1, I'm going to have 2 minus 6, so that's going to be negative. And if I plug in something bigger than root 3, like 2, again, I'm going to get something like 16 minus 12, so that's going to be positive. So I see that f is concave down, and then concave up, and then concave down, and then concave up. So it happens to alternate in this case. So running out of a little bit of room. Oops. So I'll try to just insert a page. Okay, we'll go back here. Okay, so we have, oops, that's our increasing, decreasing information. So this got a little bit out of order, but we're down to this part here. Okay, and so we need to make use of that information to write down our locations of inflection points. So we know we're going to have concave down on these two intervals and concave up on these two pieces. And we know we're going to have, looks like, 3 different inflection points. So let me just go back to here and we'll copy over this information. So we had, these were our different places where our second derivative could be 0. And we saw that the signs happen to alternate in this case. They don't always alternate. And so f was concave down and then concave up, concave down, concave up. So we have f is concave down on the intervals from negative infinity to negative root 3, as well as from, let's see, 0 to root 3. And we're concave up on the intervals from negative root 3 to 0, as well as from root 3 to infinity. And our inflection points, and there are 3 of them, occur at negative root 3, comma f of negative root 3, at 0, comma f of 0, and at root 3, comma f of root 3. So remember that f of x is equal to x over x squared plus 1. Okay, so it turns out that we get y values here of negative root 3 over 4, 0, and root 3 over 4. Okay, so using our first and second derivative, we were able to get all this information about concavity as well as about inflection points. Okay, and sometimes we'll be asked to do curve sketching next, but we are not going to do curve sketching in this particular example. We just want to look at a few more examples of things that we can sketch, as well as talking about the second derivative test. Okay, so this put together our concavity information as well as our increasing, decreasing information. So what about if we have something like this? So this is telling us to sketch the graph of a function that satisfies all of these conditions. So this is kind of moving us towards a curve sketching example where maybe we would have to figure out all the information that's here about the derivatives and then do a sketch. So let's just break apart the information that we have here. So first it's telling us that our first derivative is positive if the absolute value of x is less than 0. Remember that the absolute value is sort of like a measure of distance, so this is saying the distance between x and 0 is less than 2, which means that x is between -2 and 2. So if I'm thinking about a sign chart here, I know that the first derivative is positive, greater than 0, when x is between -2 and 2. And then we're told that the first derivative is less than 0 is negative if the absolute value of x is greater than 2, meaning the distance between x and 0 is more than 2. So this means that x is greater than 0 or x is less than -2, which means that I'm negative in these two pieces. So we also have this information that the derivative at -2 is 0. So maybe I could put that here. And I have information that the limit as x goes to 2 of the absolute value of the first derivative is infinity. So probably our derivative at 2 from this information, or I should say this information tells us the derivative at 2 doesn't exist, but it's getting larger and larger and larger, getting to a slope of infinity at 2. Okay, so we'll have to keep that information in mind. And we also have information here about the second derivative being positive everywhere except at 2. So we have positive everywhere, so it's concave up everywhere except at 2, which may be a place where our function is not defined. And then we know that f here is decreasing, increasing, and decreasing. So with this information, we'd want to try to get a sketch of our graph. So important values occur at -2 and 2, so we want to mark those off here. So I know that at -2 my derivative is 0, so I should have some kind of a horizontal tangent at -2. And I also know that my function is decreasing and then increasing from -2. So I may have something like this in mind, so to give me that horizontal tangent at -2. So now I just have to worry about what's happening next. Well, I know that I'm increasing from -2 to 2, so it's going to keep increasing. I'm going to decrease after 2, but I know I'm going to stay concave up. I also have this information about my derivative as I approach 2 going to infinity. So one way that could happen is maybe I really just have an asymptote at 2. So this is getting increasingly steep from both sides. So the derivative is going to infinity there. But notice that I've kept all of these other properties. I have my function being concave up here, concave up here. My function goes from being decreasing to increasing to decreasing, okay? But I don't have a local min or a local max at 2 because I have this situation of having an asymptote at 2, okay? It could be possible that another way this graph could look is maybe I have some kind of shouldn't draw quite, it's not quite a corner there, but maybe I have something with some kind of cusp where it really gets quite steep here, but these two things do touch. It's just that it's not differentiable there. But that's a little bit harder to draw. So I think this is one example that satisfies all of these different conditions. Okay. So let's see another important result that we have from the second derivative. So besides having a first derivative test that uses information about the first derivative to tell us where we have local mins and local maxes, we can also make use of the second derivative test. The second derivative test can be useful in many circumstances, but we'll often find that we're going to prefer to use the first derivative test to make statements about where we have mins and maxes. But what the second derivative test says is that suppose that our second derivative is continuous near C. If we have a critical point where f prime of C is 0 and the second derivative at C is positive, then f has to have a local min at C. So the idea here is that there's a horizontal tangent line at C. That's what we get from this f prime of C equals 0. And we know that the second derivative at C is greater than 0. That means we're looking at our graph being concave up near C. So that means we have a picture of something like this. where I've got this horizontal tangent down here. So we can see from this picture that this means that we're going to have a local min of our graph at that point C. If, on the other hand, our first derivative at C is 0 and the second derivative is less than 0, then we're looking at our function being concave down, and we've got a local max at C. Okay. So where we have to be careful with this theorem is if the second derivative is 0 at that point, or the second derivative doesn't exist, then this second derivative test is inconclusive, meaning C may be local max or min, but we don't know from this test. We'd need to use the first derivative test. So when we get into optimization examples, we'll see that there are some cases where the second derivative test may be more helpful or a little bit easier to use, but a lot of times we're just going to want to use the first derivative test to check for where we have local mins and local maxes. Okay, so we're just going to look at one quick example using this and then talk a little bit about a curve sketching example. So here we're being asked to practice finding local max and min values of a function using the second derivative test. So we just want to apply that test that we just had. So remember that the test starts off by saying in both cases we need to have a value where the first derivative is 0. Okay, so we need to find our derivative. So we get 6x minus 6x squared here. So we'd have to find what values are there where the derivative is equal to 0. So we'd be looking at this. And so we could do a little bit of factoring here. And so we'd get x is 0 and 1. So those are potential candidates for us to check with the second derivative test. So we also need the second derivative. So we have 6 minus 12x. So these are places where the first derivative is 0. So I'd also need to check the signs of f double prime of 0 and f double prime of 1. So f double prime of 0 would be equal to 6, which is positive. So by the second derivative test, we would have a local min at x equals 0. Since this second derivative being positive would mean we're actually concave up, so I'd have a local min at x equals 0. The second derivative here at 1 would give me 6 minus 12, would give me negative 6, so that would be less than 0. So I'd have something that's concave down, so I'd have a local max at x equals 1. Okay, so using the second derivative in this test in this case worked rather nicely, but we'll have some examples where we may end up with the inconclusive step, or it may just be a little bit more work and easier to use the first derivative test. But we should just be aware of the second derivative test so we can make use of it in certain occasions.